I would like to give a brief introduction to a spectroscopic technique used in chemistry known as NMR. NMR stands for nuclear magnetic resonance, and in particular I'd like to look at proton NMR, used for studying the protons in chemical compounds. Okay. So just a brief intro about the background of what NMR is. So the nuclei and atoms of elements possess a phenomenon known as spin. So they precess around a particular point, and when they precess, they generate a magnetic field. So we denote this local magnetic field with the symbol B. And if we expose this nuclei to an external magnetic field, which is what the NMR machine is, it's essentially a giant magnet. We also denote this B naught, this external magnetic field. Then the nuclei can either align with or against B naught. And then this will generate a spectrum known as an NMR spectrum for that particular compound. And in terms of the types, there's several different types, including proton, carbon, phosphorus, and fluorine, depending on what you want to look at. So carbons, atoms, hydrogen atoms, phosphorus, so on. An application is used for just structure determination of different molecules. Can be organic or inorganic. So organic just meaning carbon-based. And also used for diagnosing various diseases, including cancer, multiple sclerosis, and so on. And we use MRI, which is a different form of NMR. And MRI, which stands for nuclear magnetic resonance imaging, we're looking at the relaxation times of protons in water molecules of several different internal organs in the body, including the brain, the heart, and so on. So, and I'd just like to discuss an example of using proton NMR to characterize a molecule. So this is the molecular formula of methanol, CH3CH2OH. So ethanol is a type of alcohol, okay? So the homologous series alcohol, CnH2n plus 1 OH. So this is a 2-carbon intermediate with one alcohol group. And this is a spectrum, a typical NMR spectrum we'll get if we're analyzing the protons in the ethanol. So I forgot to mention that proton NMR, it will basically give a number of signals representing a number of different proton environments you have in that molecule. So we can see, looking at here, that we have 1, 2, 3 different chemical environments for the protons in this molecule. Okay? So hence we get 1, 2, 3 signals. This signal here just originates from the chemical solvent that we're using to dissolve the molecule. So typically we use TMS, which is trimethylsilane, to dissolve the molecule. And for the exact splitting, for each peak and the ratio of the signals in each splitting, or the pattern, we will use Pascal's triangle here. So this is just the first 4 rows in Pascal's triangle, referring to the proton and then the number of neighboring protons it's coupling with. So A, with no protons, here we get a singlet, so this proton isn't coupling to any protons. Here, AX2, that's 1 proton coupling with another 2 protons. So these protons are then seeing 2 other protons adjacently, so they're coupling to 2 other protons. So that's how we get a triplet for this peak. And then finally, these 2 protons are coupling with 3 other nearby protons to give a quartet, which is AX3. So, and these numbers in Pascal's triangle just represent the distribution ratio, okay, the intensity of the distribution. So, and also along here we have the chemical shift with this symbol here, and ppm standing for parts per million. And then depending on whether we have an electron withdrawing group and an electron donating group, the signals will appear either low field or high field. So oxygen is an electron withdrawing atom, so it actually de-shields the proton, and it actually exposes it to a greater amount to the external magnetic field. So that's why the protons that are closest to this oxygen atom will appear left, low field. So they're de-shielded, okay, and they'll appear a higher chemical shift. So that's just a brief intro to proton NMR.